greatest triumph of civilization is often seen as our mastery of heat. Yet our conquest of cold is an equally epic journey from dark beginnings to an ultra-cool frontier. For centuries, cold remained a perplexing mystery. Nobody had any idea what it was, much less how to harness its effects. Yet in the last 100 years, cold has transformed the way we live and work. Imagine homes or supermarkets without fridges and frozen foods, or skyscrapers without air conditioning, or hospitals without liquid oxygen. We take for granted the technology of cold, yet it has enabled us to explore outer space and the inner depths of our brain. And as we develop new ultra-cold technology to create quantum computers and high-speed networks, it may even change the way we think and interact. This is the story of how scientists and dreamers over the past 4 centuries plunged lower and lower down the temperature scale to conquer the cold, enrich our lives, and attempt to reach the ultimate limit of cold, a holy grail as elusive as the speed limit of light, absolute zero. Extreme cold has always held a special place in our imagination. For thousands of years, it seemed like a malevolent force associated with death and darkness. Cold was an unexplained phenomenon. Was it a substance, a process, or some special state of being? Back in the 17th century, no one knew, but they certainly felt its effects in the freezing London winters.
17th century England was in the middle of what's now called the Little Ice Age. It was fantastically cold by modern standards. You have to imagine a world lit by fire in which most people are cold most of the time. Cold would have felt like a real presence, a kind of positive agent that was affecting how people felt. And that fitted nicely with the most orthodox received view that natural philosophers had inherited from the Greeks, from Aristotle, hundreds of years earlier, that there are 2 agents in the world, hot and cold. They function symmetrically. They can combine or separate.
Back then, people felt at the mercy of cold. This was a time when such natural forces were viewed with awe as acts of God. So anyone attempting to tamper with cold did so at their peril. The first to try was an alchemist, Cornelius Drebbel. On a hot summer's day in 1620, King James I and his entourage arrived to experience an unearthly event. Drebbel, who was also the court magician, had a wager with the king that he could turn summer into winter. He would attempt to chill the air in the largest interior space in the British Isles, the Great Hall of Westminster. Drebbel hoped to shake the king to his core.
He had a phenomenally fertile mind. He was an inventor par excellence. His whole world was steeped in a world of alchemy, of perpetual motion machines, of the idea of time, space, planets, moon, sun, gods. He was a fervently religious man. He was a person for whom nature presented a a galaxy of possibilities.
Dr. Andrew Shidlow, a chemist with a lifelong fascination for Drebbel, enjoys his reincarnation as the great court magician. Like most alchemists, Drebbel kept his method secret. Dr. Shidlow wants to test his ideas on how Drebbel created artificial cold.
When Drebbel was trying to achieve the lowest temperature possible. He knew that ice, of course, was the freezing point, the coldest you could get normally. But he would have been aware of the fact, through his experience, that mixing ice with different salts could get you a colder temperature.
Salts will lower the temperature at which ice melts. Dr. Shidlow thinks Drebbel probably used common table salt, which gives the biggest temperature drop. But salt and ice alone would not be enough to cool down such a large interior. Drebbel was famous for designing elaborate contraptions, a passion shared by Dr. Shidlow, who has an idea for the alchemist's machine.
So here we would have had a fan which would have been turned over, blowing warm air over the cold vessels there, and as the air blows over these cold jars, we would have had, in effect, the world's first air conditioning unit.
But could this really turn summer into winter?
The idea is to stir it in as well as possible in the 5 seconds that you have to do it.
Dr. Shidlow stacks the jars of freezing mixture to create cold corridors for the air to pass through.
You can feel it's very cold. In fact, I could feel cold air actually falling on my hands, because cold air, of course, is denser than warm air, and one can feel it quite clearly on the fingers.
The vital question: would the gust of warm air become cold?
Woof, I can feel certainly a blast of cold air hitting me as that second cover was released. Well, temperature, we're on 14 at the moment. Yes, keep it going, that's definitely the right direction. I think possibly even closer still will give us a better effect, there's no doubt.
So how would the king have reacted to his encounter with man-made cold?
He would have been shocked. He wouldn't have known what's happening. He could have, in fact, been wondering whether there's some action of gods or some sort of forces, demonological forces which were in action, and he would have left hastily, freezing as he did so.
Had Drebbel written up his great stunt, he might have gone down in history as the inventor of air conditioning. Yet it would be almost 3 centuries before this idea eventually took off. To advance knowledge and conquer the cold required men with a very different mindset. King James's Lord Chancellor, Francis Bacon, was the first to apply the scientific method to the study of heat and cold. He believed it was important to conduct experiments and analyze the results, rather than rely on the established wisdom of the ancients.
For Francis Bacon, heat and cold turn out to be right at the centre of his worldview. One way of understanding why that's so is think why heat and cold matter to human beings. They really matter in the 17th century for 2 reasons. One is the weather and one is disease. There was, after all, an obvious tension in everyday experience between the healthy effects of warmth and the healthy effects of cold. Warmth made you healthy because it stopped you radiating away the vital spirits within you. But cold obviously had crucial effects against death as well. It could preserve things for immensely long times, and maybe it could preserve Francis Bacon's body too.
Bacon rarely carried out experiments himself, but his one foray into the preservative effects of the cold had disastrous consequences. He took a freshly killed chicken and stuffed it full of ice and snow to investigate how much longer the chicken meat might stay fresh. He was impressed by the results. The chicken did remain fresh for many days. Unfortunately, during the process of exposing his own body to the cold, he caught pneumonia. As Bacon lay dying, it dawned on him that his fascination with the cold was going to cost him his life.
The irony, tragedy of that rather sad experiment didn't dissuade his followers from doing more experiments on ice and snow and its vital or preservative effects. The men who followed Bacon were really convinced that if we could understand the way in which motion, cold and heat fitted together, we could save ourselves from disease, we could unlock the mysteries of the universe.
This fundamental question, what is cold, haunted Robert Boyle, who was born the year after Bacon died. The son of the Earl of Cork, a wealthy nobleman, Boyle used his fortune to build an extensive laboratory. Boyle is famous for his experiments on the nature of air, but he also became the first master of cold. Believing it to be an important but neglected subject, he carried out hundreds of experiments.
He worked through, very systematically, a series of ideas about what cold is. Does it come from the air? Does it come from the absence of light? Is it that there are strange, so-called frigorific, cold-making particles? The dominant view, certainly in Boyle's lifetime, the view that he set out to attack, is that cold is a primordial substance. That when bodies get colder, they're sucking in this primordial cold, and as they get warmer, they expel it. Boyle thought that was wrong, and he did experiments to show that it was wrong.
Boyle was curious about the way water expanded when it turned to ice. He wondered whether the increase in volume was accompanied by an increase in weight. They carefully weighed a barrel of water and took it outside in the snow, leaving it to freeze overnight. Boyle reasoned that if once the water turned to ice, the barrel weighed more, then perhaps cold was a substance after all. But when they reweighed the barrel, they discovered it weighed exactly the same.
So what must be happening, Boyle guessed, was that the particles of water were moving further apart. And that was the expansion, not some substance flowing into the barrel from outside.
Boyle was becoming increasingly convinced that cold was not a substance, but something that was happening to the particles, and began to think back to his earlier experiments with his air pump.
Boyle's idea was that the air trapped in this glass container is springy, it's elastic. As you try and compress it, it resists. Now, this is very closely linked in Boyle's program to the way he studies heat and cold, because his idea was that as substances like the air get warmer, they tend to expand. It's as though the little particles, little springs, out of which he imagined each air particle is made, are gradually unwinding, so they take up more space and they expand. Boyle's conclusion here was that heat is a form of motion of a particular kind, and that as bodies cool down, they move less and less.
Boyle's longest published book was on the cold, yet he found its study troublesome and full of hardships, declaring that he felt like a physician trying to work in a remote country without the benefit of instruments or medicines. To properly explore this country of the cold, Boyle lamented the lack of a vital tool, an accurate thermometer. It was not until the mid-17th century that glassblowers in Florence began to produce accurately calibrated thermometers. Now it became possible to measure degrees of hot and cold. Because rather than mercury, they used alcohol, which is much lighter, they made thermometers that were sometimes several meters long and were often wound into spirals. But there was still one major problem with all thermometers: the lack of a universally agreed temperature scale.
There are all kinds of different ways of trying to stick numbers to these degrees of hot and cold, and they, on the whole, didn't agree with each other at all. So one guy in Florence makes one kind of thermometer, another guy in London makes a different kind, and they just don't even have the same scale. And so there was a lot of problem in trying to standardize thermometers.
Imagine that you want to make a scale of temperature. What do you do? Well, the obvious thing to do, and this was well understood by instrument makers and experimenters in the 17th and 18th century, is to try and find something in nature which you know always has the same temperature and make that your fixed point. A better strategy even is to find two such phenomena in nature, and then you have a lower fixed point, say something rather cold, and an upper fixed point, something rather warm, and divide the degrees of temperature between into, say, 100 convenient bite-sized chunks. The problem, however, was to define a phenomenon whose temperature you guessed was fixed. So for the lower fixed point, you might choose the temperature of ice just as it's melting. And then there's an almost indefinite range of possible candidates for your upper fixed point. Isaac Newton, for example, worked rather hard on constructing what he called a scale of heat. He, for example, defined the temperature which a human can only just tolerate if they plunge their hand into warm water. It could be the normal human underarm, the temperature of the human blood, the temperature of wax just as it's melting.
The first temperature scale to be widely adopted was devised by Daniel Fahrenheit, an accomplished instrument maker who made thermometers for doctors in Holland. He used a mixture of ice, water and salt for his 0 degrees, ice melting in water at 32 degrees, and for his upper fixed point, the temperature of the human body at 96 degrees, which is close to the modern value.
One of the things that Fahrenheit was able to achieve was to make thermometers quite small. And that he did by using mercury, as opposed to alcohol or air, which other people had used. And because mercury thermometers are compact, clearly if you're trying to use it for clinical purposes, you don't want some big thing sticking out of the patient. So the fact that he could make them small and convenient, that seems to be what made Fahrenheit so famous and so influential.
It was a Swedish astronomer, Anders Celsius, who came up with the idea of dividing the scale into 100 divisions.
The original scale used by Celsius was upside down. So he had the boiling point of water as 0 and the freezing point as 100, with numbers just continuing to increase as we go below freezing. And this is another little mystery in the history of the thermometer that we just don't know for sure. What was he thinking when he labeled it this way? And it was the botanist Linnaeus, who was then the president of the Swedish Academy, who after a few years said, well, we need to stop this nonsense, and inverted the scale to give us what we now call Celsius scale today.
A question nobody thought to ask when devising temperature scales was, how low can you go? Is there an absolute lower limit of temperature? The idea that there might be would become a turning point in the history of cold.
The story begins with the French physicist Guillaume Amonton. He was doing experiments heating and cooling bodies of air to see how they expand and contract.
We're now going to put ice around our bulb and see what happens.
And he was noticing that, well, when you cool a body of air, the volume or the pressure would go down. And he speculated, well, what would happen if we just kept cooling it?
By plotting temperature against pressure, Amonton saw that as the temperature dropped, so did the pressure, and this gave him an extraordinary idea.
Amonton started to consider the possibility, what would happen if you projected this line back until the pressure was zero? And this was the first time in the course of history that people had actually considered the concept of an absolute zero of temperature. Zero pressure, zero temperature.
It was quite a revolutionary idea when you think about it, because you wouldn't just think that temperature has a limit of a lower bound or zero, because in the upper end it can go on forever, we think, until it's hotter and hotter and hotter. But somehow maybe there's a 0 point where this all begins. So you could actually give a calculation of where this 0 point would be. Amonton didn't do that calculation himself, but some other people did later on. And when you do it, you get a value that's actually not that far from the modern value of roughly minus 273 centigrade.
In one stroke, Amonton had realized that although temperatures might go on rising forever, they could only fall as far as this absolute point. For him, this was a theoretical limit, not a goal to attempt to reach. Before scientists could venture towards this 0 point, far beyond the coldest temperatures on Earth, they needed to resolve a fundamental question. By now, for most scientists, the penny had dropped that cold was simply the absence of heat. But what was actually happening as substances warmed or cooled was still hotly debated.
The argument of men like Amonton relied completely on the idea that heat is a form of motion, and that particles move more and more closely together as the substance in which they're in gets cooler and cooler.
Unfortunately, the science of cold was about to suffer a serious setback. The idea that cooling was caused by particles slowing down began to go out of fashion. At the end of the 18th century, a rival theory of heat and cold emerged that was tantalizingly appealing, but completely wrong. It was called the caloric theory, and its principal advocate was the great French chemist Antoine Lavoisier. Like most scientists of the time, Lavoisier was a rich aristocrat who funded his own research. He and his wife, Madame Lavoisier, who assisted with his experiments, even commissioned the celebrated painter David to paint their portrait. Lavoisier carried out experiments to support the erroneous idea that heat was a substance, a weightless fluid, that he called caloric.
He thought in the solid state of matter, molecules were just packed close in together. And when you added more and more caloric to this, the caloric would insinuate itself between these particles of matter and loosen them up. So the basic notion was that caloric was this fluid that was, as he put it, self-repulsive. It just tended to break things apart from each other. And that's his basic notion of heat. So cold is just the absence of caloric, or the relative lack of caloric.
Lavoisier even had an apparatus to measure caloric, which he called a calorimeter. He packed the outer compartment with ice. Inside, he conducted experiments that generated heat, sometimes from chemical reactions, sometimes from animals, to determine how much caloric was released. He collected the water from the melting ice and weighed it to calculate the amount of caloric generated from each source.
I think the most striking thing about Lavoisier is that he sees caloric as a substance which is exactly comparable with ordinary matter, to the point that he includes caloric in his list of the elements. It's very easy to talk about the quantity of heat and to think of it as a fluid, whereas to talk about the quantity of heat and to think of it as a vibration of the particles of matter, which was the other alternative, that's much more difficult conceptually.
It's a very hard model to refute, because if you can accept that there's a substance that doesn't have any weight, indeed for Lavoisier, heat, caloric, is an element. It's an element like oxygen or nitrogen. Oxygen gas is made of oxygen plus caloric. And if you take the caloric away, presumably the oxygen might liquefy. So it's a very hard model to shift because it explains so much, and indeed Lavoisier's chemistry was so otherwise extraordinarily successful. However, Lavoisier's story about caloric was soon undermined.
There was one man who was convinced Lavoisier was wrong and was determined to destroy the caloric theory. His name was Count Rumford. Count Rumford had a colourful past. He was born in America, spied for the British during the Revolution, and after being forced into exile, became an influential government minister in Bavaria. Among his varied responsibilities was the artillery works, and it was here in the 1790s that he began to think about how he might be able to disprove the caloric theory using cannon boring. Rumford had noticed that the friction from boring out a cannon barrel generated a lot of heat. He decided to carry out experiments to measure how much. He adapted the machine to produce even more heat by installing a blunt borer that had one end submerged in a jacket of water. As the cannon turned against the borer, the temperature of the water increased and eventually boiled. The longer he bored, the more heat was produced.
For Rumford, what this showed was that heat must be a form of motion, and heat is not a substance, because you could generate indefinitely large amounts of heat simply by turning the cannon.
Despite Count Rumford's best efforts, Lavoisier's caloric theory remained dominant until the end of the 18th century. His prestige as a scientist meant that few dared challenge his ideas. Sadly, this did not protect him from the revolutionary turmoil in France, which was about to interrupt his research. At the height of the Reign of Terror, Lavoisier was arrested and eventually guillotined.
The reason he was guillotined was not because of his science, but because he helped run the privatized income tax service of the French state. And there's nothing more unpopular, even in France, than a privatized tax collector. Once he was guillotined, his wife left France and eventually met Rumford when he moved to Western Europe in the early 1800s. Rumford then married her, so he'd married the widow of the man who'd founded the theory that he'd destroyed.
The marriage was short-lived. After a tormented year, Rumford left Madame Lavoisier and devoted the rest of his life to his first love, science. It would be nearly 50 years before his theory of heat and cold was finally accepted. A founder of the Royal Institution, Rumford continued to support the pursuit of science, and it was here that the next major breakthrough in the conquest of cold would occur. Michael Faraday, who later became famous for his work on electricity and magnetism, unwittingly carried out an experiment that would begin the long descent towards absolute zero. He was asked to explore the properties of a newly discovered pungent gas called chlorine. This experiment was potentially explosive, which is perhaps why it was left to Faraday. and perhaps also why Dr. Andrew Shidlow is curious to repeat it today.
We are about to undertake an exceedingly dangerous experiment in which Michael Faraday in 1823 heated this substance here, the hydrate of chlorine, in a sealed tube. Is that sealed?
That's sealed, Andrew.
That's absolutely brilliant.
In the original experiment, Faraday took the sealed tube and heated the end containing the crystals. He put the other end in an ice bath. Soon, he noticed yellow chlorine gas being given off.
Because the gas is being produced, pressure's building up. But because this side is so very cold, hopefully what we'll see is some tiny oily droplets of chlorine, liquid chlorine, being produced. It's the pressure which is causing this. Ray, this is where it starts to get dangerous. So if you now take a few steps back.
When Faraday did the experiment, a visitor, Dr. Paris, called in to see what he was up to. Paris pointed out some oily matter in the bottom of the tube. Faraday was curious and decided to break open the tube.
Right, so let's have a look inside here.
The explosion sent shards of glass flying. With the sudden release of pressure, the oily liquid vanished.
And there we are.
Is that what happened?
Yeah, that's exactly what happened. It popped open, glass flew. And can you detect the strong smell of chlorine?
I can now.
Absolutely. Well, he detected the strong smell of chlorine, and this was a major mystery for him.
Faraday soon realized the increased pressure inside the sealed tube had caused the gas to liquefy. Later, he used the same technique to liquefy ammonia gas. He noticed that on releasing the pressure, the liquid evaporated, triggering a dramatic drop in temperature. He predicted that one day this cooling might be useful.
There is great reason to believe that this cooling technique with ammonia may be successfully employed for the preservation of animal and vegetable substances for the purposes of food.
But Faraday's idea of using ammonia as a refrigerant was ahead of its time. Besides, he had no interest in commercial exploitation. Across the Atlantic, a Yankee entrepreneur had a very different philosophy and was about to commercialize coal. Frederick Tudor had a chance conversation with his brother that led him on a path to become one of the richest men in America.
The story goes at the dinner table, they were trying to decide what they had on their father's farm they could make money off of, and certainly there was a lot of rocks, but people weren't going to pay for that. So they came up with the idea of maybe ice, because some areas did not have ice. And it seemed kind of crazy at first, but it paid off.
When Tudor began harvesting ice from New England ponds, he soon realized he needed specialized tools to keep up with the huge demand.
We had the saws, and the saws were improvement over the old wood saws. They have teeth that are sharpened on both sides and set, so it cuts on both the up and the down stroke. And a crew could clear a 3-acre pond easily in a couple of days.
Tudor's dream to make ice available to all was not confined to New England. He wanted to ship ice to hot parts of the world like the Caribbean and the Deep South.
When Tudor first tried to convince shipmasters to put his load of frozen water into the ships, they all refused because they told him that water belonged outside the hull, not inside. So he had to go find other investors to get the money to buy his own ship, and he bought a ship by the name of the Favorite.
New England became the refrigerator for the world, with ice shipments to the Caribbean, the coast of South America, and Europe. Tudor even reached India and China. Watching the ice cutters working Walden Pond, Henry Thoreau marveled that water from his bathing beach was traveling halfway round the globe to end up in the cup of an East Indian philosopher. Tudor, who soon became known as the Ice King, began using horses and huge teams of workers to harvest larger and larger lakes as the demand for ice grew. During the latter half of the 19th century, the ice industry eventually employed tens of thousands of people.
Tudor became the largest distributor of ice, and he became one of the first American millionaires. And we're talking about one of his ships going to the Caribbean, giving him a profit of $6,000. Now, this is in a time period when people were earning $200 to $300 a year, the average family. So someone earning thousands of dollars was just inconceivable. And that would be losing 20% of your ice when it got there. There was still huge amounts of profit.
Tudor's success was based around an extraordinary physical property of ice. It takes the same amount of heat to melt a block of ice as it does to heat a similar quantity of water to around 80 degrees centigrade. This meant that ice took a long time to melt, even when shipped to hotter climates. What started out as a small family enterprise turned into a global business. Frederick Tudor had industrialized coal, in the same way the great pioneers of steam had harnessed heat. By the 1830s, the Industrial Revolution was in full swing. Yet ironically, it was not until a small group of scientists worked out the underlying principles of how steam engines convert heat into motion that the next step in the conquest of coal could be made. Only after solving this riddle of heat engines could the first cold engines be made to produce artificial refrigeration.
How much useful work can you get out of a given amount of heat? By the early 1800s, that had become the single most important economic problem in Europe. To make a profit was to convert heat into motion efficiently, without wasting heat and getting the maximum amount of mechanical effect.
The first person to really engage with this problem was a young French artillery engineer, Sadi Carnot. He thought that improving the efficiency of steam engines might help France's flagging economy after defeat at Waterloo. Working at the Conservatoire des Arts et Métiers, he began to analyze how a steam engine was able to turn heat into mechanical work.
The originality of Carnot's treatment, in my eyes, is essentially that he shows that in order to extract energy, to extract work from a heat engine, you need a high temperature source, which is the boiler, and you need a low temperature, which is that of the condenser. And the essence of the heat engine for Carnot is that heat passes from the high temperature of the boiler to the low temperature of the condenser.
In steam engines, it looks as though heat is flowing around the engine, and as it flows, the engine does mechanical work. The implication there is that heat is neither consumed nor destroyed. You simply circulate it around and it does work. So there the analogy would be between heat in a steam engine and water in a water wheel, as though it's the flow of heat that's actually getting the work done in a standard steam engine.
Carnot likened this flow of heat to the flow of water over a water wheel. He saw that the amount of mechanical work produced depended on how far the water fell. His novel idea was that steam engines worked in a similar way, except this fall was a fall in temperature from the hottest to the coldest part of the engine. The greater the temperature difference, the more work was produced. Carnot distilled these profound ideas into an accessible book for general readers, which meant it was largely ignored by scientists, instead of being heralded as a classic.
Well, this is the book. It's Carnot's only publication, Reflections on the Motive Power of Fire of 1824. A small book, 118 pages only, published just 600 copies, and in his own lifetime it's virtually unknown. 20 years after the publication, William Thompson, the Scottish physicist, is absolutely intent on finding a copy. He's here in Paris, and the accounts we have suggest that he spends a great deal of time visiting bookshops, visiting the bouquiniste on the banks of the Seine, always asking for the book, and the booksellers tell him they've never even heard of it.
Back then, William Thompson, who would later become Lord Kelvin, a giant in this new field of thermodynamics, was impressed by Carnot's idea that the movement of heat produced useful work in the machine. But when he returned home, he heard about an alternative theory from a Manchester brewer called James Joule.
Joule had this notion that Carnot was wrong, that heat wasn't producing work just by its movement. Heat was actually turning into mechanical work, which is a very strange idea when you think about it. We're all now used to thinking about energy and how it can take all different forms. But it was a revolutionary idea that heat and something like mechanical energy were at bottom the same kind of thing.
The experiment that convinced Joule of this was set up in the cellar of his brewery. It converted mechanical movement into heat, almost like a steam engine in reverse. He used falling weights to drive paddles around a drum of water. The friction from this process generated a minute amount of heat. Only brewers had thermometers accurate enough to register this tiny temperature increase caused by a measured amount of mechanical work.
Joule's work mattered because it was the first time that anyone had convincingly measured the exchange rate between movement and heat. He proved the existence of something that converts between heat and motion. That something was going to be called energy. And it's for that reason that the basic unit of energy in the new international system of units is named after him, the joule.
This apparent contradiction between Joule and Carnot was eventually resolved by Thompson in what would later become known as the laws of thermodynamics. The first law, from Joule's work, states that energy can be converted from one form to another, but can never be created or destroyed. The second law, from Carnot's theory, states that heat flows in one direction only, from hot to cold. In the second half of the 19th century, this new concept of energy paved the way for steam power to artificially produce coal. The flow of heat from hot to cold drives any refrigeration cycle, whether it's a modern fridge or a steam-powered ice-making machine. In the first stage of this cycle, gigantic pistons compress ammonia gas into a hot liquid. the hot, liquefied ammonia is pumped into a condenser, where it is cooled and fed into pipes beneath the water tanks. In the next stage, the liquid ammonia evaporates and the temperature drops. As the ammonia absorbs heat from the surrounding water, gradually the tanks of water become blocks of ice. By the 1880s, many towns across America had ice plants like this one, which could produce 150 tons of ice a day. For the first time, artificially produced ice was threatening the natural ice trade created by Frederick Tudor. America's appetite for ice was insatiable. Slaughterhouses, breweries, and food warehouses all needed ice. Animals were disassembled on production lines in Chicago, and the meat was loaded into ice-cooled boxcars to be shipped by railroad.
Livestock on its way to the great meat-packing centers of the nation, to markets everywhere. Food of every sort, safely and quickly delivered in refrigerator cars.
From New York to Los Angeles, restaurants were able to serve fresh steaks thousands of miles from where their meals once roamed. As fruit and vegetables became available out of season, urban diets improved, making city dwellers the best-fed people in the world. And to keep everything fresh at home, the Iceman made his weekly delivery to recharge the refrigerator.
Refrigeration makes a tremendous difference in people's lives. First of all, in the diet, what is possible for them to eat. They can go to the store once a week. They don't have to go every day. They can obtain at that store foods that are from almost anywhere in the world that have been transported and kept cool, and then they can keep them in their own home.
Eventually, the Iceman disappeared as more and more households bought electric fridges. These used the same basic principles as the old ice-making machines. Heat from the food inside is drained away by the evaporating coolant and is dumped out the back. The electric pump drives this cycle of compression, evaporation, and condensation. And that's how the fridge got its hum.
The electric power companies loved refrigerators because they ran all day and all night. They may not have used that much power for each hour, but they continued to use that. So one of the ways that they sold rural electrification was the possibility of having your own refrigerator.
In the early days, the fridge's icebox was used to freeze water, nothing else. Freezing was seen as having the same damaging effects as frost. The man who had changed this idea forever was a scientist and explorer called Clarence Birdseye. In 1912, Birdseye set off on an expedition to Labrador, and the temperature dropped to 40 degrees below freezing. The Inuit had taught Birdseye how to ice fish.
You get a hole out in the ice which could be several feet thick, and you fish with a pole and a line down below and bring the fish up. And as you do that, he found that they would freeze in this terribly cold air almost before they hit his shoulder. When you went to cook this fish, it tasted just as good as it's fresh. And he couldn't figure that out because when he froze fish at home, they would taste terrible. So when he got back home, he finally tried to figure out what was the difference between this quick freezing and the usual freezing.
Under closer examination, he could see what was happening to the fish cells. With slow freezing, large ice crystals formed, which distorted and ruptured the cells. When thawed, the tissue collapsed, and all the nutrients and flavor washed away.
That's the mushy strawberry syndrome. People freeze the strawberries that they pick in their garden, and then they put them out on the table the next day, and they collapse. They're all mushy.
But with fast freezing, only tiny ice crystals were formed inside the cells, and these caused little damage. It was all down to the speed of the freezing zone.
What Birdseye found out is if you can get through this zone very quickly, flash freezing or quick freezing, you avoid this ice crystallization. And that makes it possible for the food, when it's unfrozen and cooked, to taste just as good as fresh.
The basic concept was simple, but it took Clarence Birdseye another 10 years to perfect a commercial fast freezing technique that would mimic the natural process he'd experienced in Labrador. In 1924, he opened a flash freezing plant in Gloucester, Massachusetts, that froze freshly landed fish at -45 degrees.
And he then extended that to all sorts of other kinds of meats and produce and vegetables, and almost single-handedly invented the frozen food industry.
Fridges and freezers would eventually become icons of modern living. But there was a less visible cold transformation happening at the same time. This would also have a huge impact on urban living. The cooling of the air itself. 3 centuries had passed since Cornelius Drebbel had shaken King James in Westminster. Now, at the dawn of the 20th century, air cooling was about to shake the world.
Tell me, what is the lowdown on this air conditioning thing?
Now you've started something by asking me that.
Air conditioning was about to transform America, and the person responsible was Willis Carrier, whose important breakthrough passed into comfort-cooling mythology.
Let's go back to that foggy night when a young engineer named Willis Carrier sought the answer to a problem: the effects of humidity, of moist air, on industrial production.
Fog. Maybe that's the answer. Let's see. Fog is water vapor that's been condensed. That's because the air has become cooler, and cool air can't hold as much moisture as warm air. Maybe that's the way to reduce humidity. Cool the air and condense the moisture. It might work.
Control of humidity through control of temperature. That was Willis Carrier's idea.
Carrier is sent to Brooklyn for a very special job in 1902. The company that publishes the magazine Judge, one of the most popular full-color magazines in America at this particular time, is having a huge problem. It's July in Brooklyn, and the ink for which they use on their beautiful covers is sliding off the pages. It will not stick because the humidity is too high. Carrier, using some principles that he's been developing as a young new employee of this fan company, finds a way to get out the July 1902 run of the Judge magazine, and from there he begins to eventually build his air conditioning empire.
The demand for air conditioning gradually grew. In the 1920s, movie houses were among the first to promote the benefits. People would flock there in summer to shelter from the heat.
The movies are wildly popular, and the air conditioning certainly helps to attract an audience, especially if they happen to be walking down the street on a horribly hot day and they duck into this movie theater and have this wonderful experience.
Air conditioning became increasingly common in the workplace too, particularly in the South, where textile and tobacco factories were almost unbearable without cooling.
When employees breathe good air and feel comfortable, they work faster and do a better job.
I think some people think that these were nice, compassionate employers who were cooling down the workplace for the workers, but of course nothing could be further from the truth. That was an inadvertent byproduct, but actually this was a quality control device to control the breaking of fibers in cotton mills, to get consistent quality control in these various industries, to control the dust that had bedeviled tobacco stemming room workers for decades. I think the workers obviously went home and to their unair-conditioned shacks in most cases, and talked about how nice and cool it was working during the day. Well, as anybody will tell you who's lived here for very long, even today in the age of air conditioning, there's still plenty of sun and sweat and humidity. It's something you just have to deal with.
It's silly to suffer from the heat when you can afford the modest cost of air conditioning.
By the 1950s, people were air conditioning their homes with standalone window units that could be easily installed. This wasn't just an appliance, it offered a new, cool way of life.
Walking down a typical southern street prior to the air conditioning revolution, you would have seen families, individuals outside. They would have been on their porches, on each other's porches. There was a visiting tradition, a real sense of community. Well, I think all that changes with air conditioning. You walk down that same street and basically what you'll hear are not the voices of people talking on the porch, you'll hear the whir of the compressors.
Guess what we've got? An RCA room air conditioner. I'm a woman, and I know how much pure air means to Mother in keeping our rooms clean and free from dust and dirt.
Control of the cold has transformed city life. Refrigeration helped cities expand outwards by enabling large numbers of people to live at great distances from their source of food. Air conditioning enabled cities to expand upwards. Beyond 20 stories, high winds make open windows impractical. But with air conditioning, 100-story skyscrapers were possible.
Technologies emerge which not only worked to insulate human society against the evils of cold, but turned cold into a productive, manageable, effective resource. On the one hand, the steam engine, on the other, the refrigerator. Those two great symbols of 19th century world, which completely changed the society and economy of the planet. All that is part of, I think, what we could call bringing cold to market, turning it from an evil agent that you feared into a force of nature from which you could profit.
The explosive growth of the modern world over the last 2 centuries owes much to the conquest of cold, but this is only the beginning of the journey down the temperature scale. Going lower would be even harder, but would produce greater wonders that promise extraordinary innovations for the future. With rival scientists racing towards the final frontier, the pace quickens and the molecular dance slows as they approach the holy grail of cold, absolute zero.
Stay with us as the race for absolute zero is hotting up next on BBC4 in part 2 of our double bill.